is going well. Okay. So this was a good warm-up, the quiz, to remember what we started last time. Surface waves, which are actually very, very important in both seismology and in non-destructive evaluation. And then I asked you to compare them. Let's just really bullet it. You already thought about it right now. Talk about a few differences they have. So what did you write about? What are some of the differences if we have bulleted items? What did you write in your quiz? Yeah, so the first thing is what we had explained about propagation direction and particle displacement. I don't repeat S and P wave, but kind of for surface waves, you saw that the particle displacement, it is a retrograde ellipse. It has two components, both like a P wave and a SV wave, and they're propagating together. What else? How about in terms of velocity? Last time, we kind of casually derived the equation which gives us the velocity of surface waves. And what's the main thing to remember?
That relates to the Poisson's ratio, and the velocity of the surface wave is smaller than the S wave.
Right. So this is something to remember. I guess you don't forget. And then we learned that it is not dispersive in half a space, in elastic half a space. And when I say not dispersive, I mean, what do I mean by that? It doesn't depend on frequency, right? Because in the equation there was only velocities of S and P, and there was no mention of K, wave number, right? Okay. What else?
Just a question.
Mm-hmm.
What does like elastic half space? It just means that it's not infinite in those directions.
Mm-hmm. It's an ideal, it's like, when you learn in soil mechanics, Boussinesq theory, when we have a load on elastic half space. It's like you have the same material all over and you don't know where it ends. Mm-hmm. Good question. Okay, what else? I hope you wrote a few other things. Amplitude. So what about amplitude, Yingjun?
Amplitude, the radio waves contains the largest amplitude, which means actually it contains the main energy.
When you say largest amplitudes, are you talking about amplitudes on the surface?
Yes.
Right. So what happens is that on the surface, the Rayleigh wave, the geometric spreading is much slower than body waves. So because of that, you are getting a large amplitude. Do you remember how does it change? Let's say if this is distance, this is source. This is how seismologists always show source. Do you know how the geometric spreading of Rayleigh waves changes with? Yes, thank you. So this is how it changes. So very slowly. And because of that, when you see in a record, it has a very large amplitude. What else? So on the surface, it's larger than PNS. And what else? Something very important is missing. But this is kind of attenuation, right? When we are talking about amplitude, it's
So you're not able to much express.
yeah. What type of attenuation are you thinking? That spreading. I mean, that's how we compare them. Because otherwise, if you think about the intrinsic attenuation, I mean, it's the same material, and this is also it's a function of Poisson's ratio and the velocity. So that is not that much different, right?
Boundary conditions and the fact that the motion is limited to a thin amplitude surface.
Right. Actually, probably the most important thing about surface wave is that the motion is contained to the near surface region. And what did we say? That it's about, it's about, I mean, it's actually like that. It's not maximum on the surface. So we had two components. We called this U1 and called this U2. And you saw that U2 was larger than U1. And kind of at about 1 lambda, it becomes very small. So the motion is confined to, let's say 1 to 1.5 lambda within the free surface. No, from the free surface. From the free surface. So now this is the theory. What do we do with it? And this is what we want to talk about today. Let's just start with something very simple. So this is from my own work many years ago. So there is a way, if we have a hammer, let's say, just very simply, if you have a source, and if you have two receivers on the surface, and if you, I'll show you how, but if you look at the velocity of surface waves, let's say for this system, where we have a concrete slab over a subbase. This is, Shane is not a civil engineer, so in pavements, when you have a concrete rigid pavement, it makes a lot of noise when you drive on it. A lot of times we have a slab over some earth materials which have lower properties than concrete. So this is a kind of a cartoon showing a rigid pavement, a simple one. So if we do that, we can get a velocity versus wavelength curve. This is called dispersion curve. Why is that? Because I told you that the velocity of surface wave is not dispersive. This is when we have a half space. What happens when you have layering in your system? So we have a layer of concrete over a layer of soil with wave velocities VR1 and VR2. The hammer is creating different frequency components. So different waves of different frequency are going to propagate. So let's first think about the high frequency components. A hammer creates different components at the same time. It has a broad range of frequencies, a broad spectrum. Okay, is this clear for everyone? Now let's focus on high frequency. When I say high frequency, is the wavelength large or small? Small. So if I just focus on the high frequency part, for both receivers, so if I filter the other low frequency and I'm just focusing on the high frequency, the surface wave of high frequency will be only traveling through concrete. Do you agree? Because it's only propagating within the first lambda of of your medium, and this is concrete. You agree? So if I measure the velocity for these wavelengths, for this range of frequencies, the velocity that I'm going to get will be just the velocity of concrete. Think about this a little bit. So it's said that, yes, of course.
To say a sentence again.
So, when you just focus on the high frequency content, that means the wavelength is small, it's tiny. Okay. If I measure the velocity of the high frequency content, just the velocity of the high frequency content, it's possible. I'll show you. Then this velocity corresponds to the velocity of concrete only, because the wave has been traveling only through concrete. Is this clear for everyone? This is clear? Okay. So now, if we then focus on a little bit larger wavelengths or lower frequencies, they start leaking into the second layer, right? If it is very, very low, the lower frequencies, they really go into the lower layer. And if it is really, really low, it will be mostly in the lower layer. So then you are basically measuring velocities here. This red gives you the velocity of here, the whole thing, and then you have the green part, which gives you a velocity here. So Rayleigh waves are not dispersive in a half space, but if you have a layered medium like what we have here, then you see that the velocity, so the curve here is velocity versus wavelengths. So it is either velocity versus wavelengths, or it is velocity versus frequency. In either case, this is called the dispersion curve. And the beauty of surface wave testing is that you are on the surface, but the velocity you are measuring is not only the velocity near the surface. If you use the right frequency, you can get the average velocity for the whole layer. And this has sparked a new way of testing in non-destructive evaluation. The paper I ask you to read is from the person who pretty much developed this as the first person who did that. This is in the institute I had my first academic job long time ago. So there is before explaining you this, there is something very neat about this. If we are only interested in the velocity of concrete, we can get it right very easily. And basically, this part is the velocity of concrete, and then this will go towards the velocity of the second layer. So in a very simple case of two-layer system, you don't need to do any kind of inversion, any kind of back calculation like in tomography. It becomes very simple. So the guy, Sohail Nazarian, who I gave you the paper to read, did you get a chance to take a look at this paper a little bit? No? Okay. He also developed a kind of a tool, an equipment that you can bring it to the field and very easily measure the velocity of surface wave. And this is how it looks like, or at least it looks like 5-6 years ago, where you have a hammer. So when I say hammer, it is not necessarily a hammer. This is, this is the source here. And then there are two receivers, and in these feet, there were also moisture temperature measurement system. So then, what you would do, you basically create the dispersion curve. I'll show you how in a second. But you may remember that at some point I asked you to do a homework where we were using the phase, and you use the phase to calculate velocity. The reason for that is here, because I wanted you to be able to relate to that. So here you look at the dispersion curve, and you basically average the velocity over a thickness, and you report it as the modulus of the first layer. This is possible, and it's much better than doing it just looking at the direct wave, like for example in Mira. So in Mira, when you measure that velocity, it is really direct wave, going from one transducer to the other. It's not telling you really what's the average velocity is inside the material. Here, this is a different kind of velocity. It's telling you what's the average velocity in this layer depending on the frequency. Is this distinction clear somewhat? Why this is a kind of a better test? Okay. So this was a very simple 2-layer case, but the typical process of surface wave testing is the following. First, we need to generate this dispersion curve, which it looks something like that. You have phase velocity versus wavelengths or frequency. This could be frequency.
What's the phase velocity?
Phase velocity, this is a good question. Phase velocity is velocity, but which is a function of frequency. So to make the distinction between this velocity and the other velocities, people use the term phase velocity. It is the velocity of a frequency component. I like to make this analogy always when I explain for the first time what's phase velocity. Have you ever been driving in, I know you did, in New Jersey on turnpike? Any turnpike? Do you ever drive on a highway? Or people? If you drive on a, have you been driving on a large highway? I know you have had a lot of driving on highways. Okay, so think about this way. If you like to speed, and you don't want to be caught by the police, okay, what do? I've learned to do this in New Jersey, so I guess Tiffany knows the answer to that. What do? What's the best way? Come on, people, you don't want to speed? What's the best way? Okay, let's cut it short. You have to stay with others.
Yeah.
Because if you ever decide to speed from now on, this is not, is it recording? Okay, the best way in New Jersey not to be caught by police is to stay with the crowd. Otherwise, if you're going fast by yourself, you're going to get a ticket. So you often on turnpike, you see batches of cars who are traveling kind of together. Okay, think about this as a particles during a wave. Think about this as energy being transmitted from one point to the other. Now, how does this relate to phase velocity? This batch of car all together, the envelope, the whole thing has a speed. Don't you agree? If you go very far and you don't see the individual cars inside, you see that there is a speed. This is called group velocity. That's an average group velocity. However, if you're inside this batch, you notice that each car has its own speed. You are not going always at the same speed. You have your individual speed. And that's more like a phase velocity. So each component in a packet of wave, if it has a different frequency, has a different velocity. In surface wave, because it's dispersive, because it's going inside another layer just because of this frequency. So it has a slightly different velocity. But as a whole, also there is a velocity which actually we call group velocity, and we separate one from the other. So phase velocity is the velocity of individual frequency components. Is this clear, everyone? I hope you remember this. Do they learn this anywhere else?
What?
This way of driving.
I don't know. I haven't been to too many places to notice.
Yeah, okay. So when the first thing we do is to create this dispersion curve, and I'll show you how we do it. So you really have to look at different frequency components and measure their velocity. And if you assemble the whole thing together, this is what you get. It's not as easy as it looks like, because it's very hard to have a very broadband source. So typically what happens is that you go with a large hammer for low frequencies, with a small hammer for higher frequencies, and you have to assemble this whole thing together. You know that the larger a source is, the lower would be the frequencies, right? Yes? So if you drop a big ball, the frequencies are much lower than when you drop a small ball. You can even know from experience of hearing things, right? In terms of frequency you hear, a big thing has a hollower sound than something very, very small when it hits, right? So the first thing and most straightforward thing is to do this dispersion curve and get this kind of curve here. Then the next thing is what we call inversion. So you have this dispersion curve and you want to get the shear wave velocity profile. People tend to use this relationship I gave you last time and always report this in terms of shear wave, because this is what in engineering applications shear wave velocity is the parameter everyone needs for site characterization, etc. So this is why. You typically assume a Poisson's ratio and density and you get your profile. And they have shown that this assumption is not affecting your results as much, so it's kind of common practice. When I say inversion is you start with a model of a velocity, and then let's say you take a model. From the model, you calculate the dispersion curve. And then you calculate it, and then you compare it. You compare it with the dispersion curve you have gotten in the field. Maybe it's better to. You compare it with what you have, and then you try to measure the error, try to fix it. Then you go back to calculate the next profile, and you do it as many times until the two very, very well match. We are not really going to talk about inversion here because, as you may expect, it's its own process, but I want to show you how we assemble dispersion curve, how you calculate basically this dispersion curve that we are looking at.
Dispersion curve, that's what we saw before with the concrete and the pavement.
Mm-hmm.
So the dispersion curve is just pretty much showing the distribution of the velocity with depth for a layer system.
Mm-hmm. Why do we need to do inversion? The problem is when you go to lower frequencies, these also include the velocity of the top layer. So this is not so beautiful. I mean, what you get is not immediately transferable to a profile. So you have to go from dispersion curve to the profile. Question? Mahbube? By now you should know why, what is dispersion, and you should know why we need inversion. are these 2 points clear to everyone? Why in now for the first layer you don't need inversion, but if it is a little bit more complicated, you need to invert.
Well, I feel like I'm understanding like the fact that we need to separate it and use inversion in order to understand the lower layers, but
for the top layer we don't need.
right. But dispersion is just when your velocity is dependent on your frequency.
Right.
So we really only need inversion for dispersion when we have different.
Which is almost all the time.
Okay.
I mean, we use surface waves to actually get information about layering. If we knew that it's elastic half space, no one wanted to know anything, right? You would take one small core, you would test it, and then you were happy with it.
Right.
So the whole idea of using these methods is to look a little bit deeper. In NDE, we use it a lot of times for material characterization. So it's the only place where you don't use really inversion if you are only interested in the first layer. But anywhere else, surface wave needs to be inverted. So for pavement, for example, this idea never flew, but there is a large version of this equipment which we had, and I worked on the 2-year project with it, where we compared that against FWD. It's much better than FWD, but since it's harder, it wasn't really widely adopted. TxDOT uses it, but other DOTs, they never adopted that. Because it's harder. FWD, they understand, it's easy for them, they drop a weight, they look at deflections, but there are 2 sources, they're geophones, you have to lower them, and then you have to go through inversion, and they just, right.
And what's this one? It's PSPA.
Yeah, it is called, I forgot, it's called Portable Seismic Property Analyzer.
Yeah,
it's called PSPA. Mm-hmm. The developer is the same guy I gave you this. He's a good friend, really dear friend, and former colleague of mine. So, so how does it all work? How do we get dispersion curve? So, the process of surface wave analysis is sometimes called spectral analysis of surface waves, because everything happens in the frequency domain. I want you to pay attention and walk really with me. It's very simple, and you have done it in homework number 1, but we need to just go through it once and you see.
I have a little trouble understanding. So the whole thing about inversion is that the depth of the layers is very, very important for calculating the second layer properties. But how do we know what frequency to work with to determine the velocity in the first layer when we don't know the thickness? What range of frequency we're supposed to work with when we don't even know what the thickness of the first layer is?
Here you mean?
Yeah.
Here. So if you have this 2-layer system, then when you have when this layer ends and the other layer starts, you see this change in the dispersion curve.
Oh, just by looking at
it. Because it's when it goes, we don't look at it. It is you can program it. You can automate it. It's you can see here is constant, and all of a sudden it's changing. So you can use this to program it. Put a threshold. If it becomes, I don't know, 5% less than that, that's when you have it.
Depth, so why do we have
we don't know the depth.
Can
That's
we
the thing.
calculate it with that section where it changes?
We don't know. Well, we don't really know this in advance. Not necessarily. You don't. When you go to the field, you don't know how thick is your section, and you don't know what's the property. So they are both unknown.
Well, we know the. Same with that, so we can't determine the velocity of in the first layer with that data?
Yes, you can. But you see, this is a real data. This is from my own work. So this is how the real data looks like. So you can program it and say, okay, if there is a sudden change here, that's where you just cut it and you say this is the thickness. If you don't know the thickness beforehand, and there is no way to know it, to limit it, you can use the shape of the dispersion curve. But actually what I did when I went there, I said, no, why do we do that? This is complicated. Why don't we use these two as impact echo and plug in this velocity into that and get the thickness from impact echo? It's much better. And then bring the thickness back to get the average modulus. We have a paper in 2007 or something with Sohail on that. So they are both unknowns. When you do surface wave testing, the layering and the modulus with thickness are both unknowns. We don't know in advance. If we know, it makes everything easy, but we don't know.
No, I just thought based on the first section you could determine the depth, and then you didn't need like inversion. So no, okay.
What do you mean based on first section? But this is exactly the same thing. You mean when, because this is constant and then it changes?
Is there any kind of like relationship between the depth and lambda?
The depth, no. The lambda, you know, it is velocity over frequency.
Yeah, but I remember when we were doing impact and there was like a relationship between the depth and the lambda, and you said like the depth is 2 lambda, something like that. So there's no relationship here.
I am not sure I understand it. So the
like
wavelength is a function of the wavelength is a function of velocity and frequency. Yeah. And of course, because it's surface wave, as long as the wave is completely contained inside concrete, you will have pretty much a constant velocity, and then it starts to change slowly, right? But it's not. I mean, this is a schematic. It's not clear cut. So you need to program this. You can say, okay, if the velocity if the standard deviation is so and so, and it increases to that, then that's where you cut it. So from that, you can kind of also guess where the thickness is. You understand? It looks very easy when you look at it, but I've worked in the field. It's not always very straightforward. I mean, you have all sorts of things going on, and they can create some strange things. So to automate it, you have to make some rules. If you are only interested on the first layer, you really don't need inversion. You get dispersion curve, you get these values, and you put some sort of a rule here. Right, and you can always use, as I said, impact echo. And this is what I added to that, why not using impact echo and try to make this better. Is this clear for everyone, this conversation? Yeah. So because from impact echo, if you know the velocity, it's easy to get the depth. So kind of you can combine them both into one package. Yeah. But typically, I mean, even for pavements, you need to have different layers. So here you are looking at how layering looks like and how is the shear wave velocity with depth. So whenever there is a big change of layer, shear wave velocity is changing, and that's what people are interested in. For example, when you are doing site characterization before designing a building, you want to know the shear wave profile in an earthquake-prone region, for example, right? It's clear that before the way earthquake amplifies and comes to the surface has a lot to do with the shear wave profile near the surface. So civil engineers are very interested in the shear wave profile near the surface to be able to see how the shaking from the bedrock is amplified when it gets to the surface. It kind of works as a transfer function going from bedrock all the way up. And that's why you need this kind of shear wave profile. Okay. Did I answer your question? Yes, Mahbube?
Yes.
Okay, great. So now let's see how do we get this dispersion curve? How does it work? This is kind of an old-fashioned. I took it from the data. Pay attention that it says portable microcomputer, like the wording. It's when everything was very basic. But the way surface wave testing is being done is that you have a source, and then you have a series of receivers. In this case, there are geophones. They can be accelerometers depending on the frequency you are interested in. The way we do this is pretty much what you do in time domain to get velocity. What did we do? We used cross correlation. In surface wave testing, we use cross power spectrum. So I call this, let's say we consider two receivers, receiver 1 and receiver 2.
I'm sorry, what is that? Is S for the source?
It is cross, I write it down, it's cross power spectrum.
What's the symbol of?
S. I'm just using the same symbol Sohail is using without, so that when you read the paper, it's the same thing. This bar on top of it is the average. Now, cross power spectrum is nothing else but the frequency transform, the FFT of cross correlation. And remember that I told you that when you have some sort of convolution or cross-correlation type, in frequency domain, it will be just multiplication. So it's very simple. So we just multiply the spectrum of the first receiver. So this R stands for receiver. So this is like R1, R2, R3, R4. So this is the frequency spectrum of the first receiver, and we multiply this by the frequency spectrum of the second receiver, but conjugate. So this is the frequency representation of cross-correlation. Because the reason is you want to get velocity of each frequency component. So we do everything in frequency domain instead of time domain. Makes sense? Do you remember that once I asked you in a homework, there were two little signals. You converted this and you calculated the phase as a function of frequency, and then you subtracted the phase. So this is pretty much the same thing. That was only one component, and now to be able to do it for the whole signal, we have to first go to the frequency domain. Okay? So typically, you do this for several receivers. They are both R1 and R2 at distance d, and the distance between source and the first receiver is d. This is a common convention, that this distance is equal to that. This is important in surface wave testing. So depending on this spacing, you may get better or worse results. There are papers just written on what should be the best spacing, but this is a good one. Some people say the distance between 1 and 2 should be larger, I think including my advisor. But I think equal distance is a good way to start. So if we have several of these measurements, you have to average them. So if we have n, we just average them in frequency domain to get the average cross power spectrum. And then for for this, we can also define a coherence function. Which is kind of a, it's similar to cross-correlation coefficient. It's, if you normalize it. So the absolute value of SR1, R2, but we normalize it by the multiplication of kind of cross-power spectrum of each receiver with itself. Sometimes this is called not cross-power spectrum, but auto-power spectrum.
What is the auto-power spectrum? Just the SR.
Auto-power spectrum is when you calculate this only, but for the same receiver. So R1 and R2, I mean, it's the set for the same receiver. It's kind of an absolute value of the same receiver. Okay. Now, in the time domain, when we calculated cross-correlation, we took the time delay out of it. Here, we calculate this cross-power spectrum, and it's a complex number. So the phase of cross-power spectrum is the frequency domain equivalent of lag time. But it is phase because we are in frequency domain. So it's nothing else but the tangent is. So it is tangent inverse of the this is R1, R2. So we are doing everything that you did in the time domain, only in frequency domain. So then we have phase as a function of frequency. This part you have already done. Now we want to calculate the velocity at each frequency. How do we do that? You just like what you did before. The time delay is phase over omega, right? This you have done in homework number 1. And now we have the time delay for each frequency component. So then we say that, okay, the velocity is, so this is like phase velocity, or CR as a function of f is distance over time delay. So it would be d over what we have.
So this distance is
Distance between two receivers. This d in the here. It's very, very similar to what you are doing cross-correlation in time domain. We are just doing this in frequency domain. Just because every frequency component may have a different velocity, and has. That's why instead of cross-correlation, we calculate cross-power spectrum. We calculate phase of cross-power spectrum, which is phase shift. In cross-correlation, you get lag, right? Time lag. Here you get phase shift. And this, the relationship between phase and time delay, this you have seen before, and then you just get velocity. That's how it is. It's very, very simple. So then for every frequency component, you have a velocity. That's how we get dispersion curve. And let's also write down the wavelengths, which will be this velocity right over frequency. So you plot phase velocity versus frequency, or you use lambda. Either way is it doesn't matter. The reason they make it opposite is because lambda and depth it's related, so it is nicer, but it could be either way, so we shouldn't be confined with that. So any question? So you see the concept is actually very simple. It's the distance between two transducers. Remember, you have two transducers, and the wave is coming from the source, passing one, going to the other. So what you are doing, you are basically in frequency domain, you are cross-correlating these two. But for every frequency component, so it is as if you would do a spectral analysis, and then you would just focus on every single frequency window. To do this all at once, this is the procedure to do. It's very simple. I think, right, is it clear? Yes? So, now, in practice, there are a few things that you have to be careful about. For example, this is what you have seen in homework number 1, and that is that when you get the phase shift from cross-power spectrum, it will be wrapped like that, right? So you need to, this you also had in the homework, you have to unwrap it. This I've explained to you during the signal processing, but that means that, if you have a few cycles before a point, you just open it up, you unwrap it. So here, this is an example that point A here is 100 degrees. When you unwrap it, it's actually 980 degrees because there are 3 cycles before it, right? So this is this process of unwrapping that has to be done to be able to calculate, and you did it in homework number 1. And then the coherence function is used to throw away the part of the data which is noisy. So the way to do it is you calculate the cross-power spectrum and you calculate coherence at the same time. And you put a threshold. I mean, here is a strange threshold, but you say, or whenever your coherence is dropping below a certain threshold, you ignore that data in the phase. Because the two sensors, they are not far from each other, and the signal which goes from here goes here. So if there is no noise, they should be coherent. If there is a big problem when the coherence function is dropping, that means that the data is bad. There is some noise in that certain frequency. So before going to inversion process, people you get rid of that part of the data and you interpolate. So here you say, okay, instead of going with these wiggly lines, I just go like that. You kind of do some sort of filling. Inversion of surface waves are not very simple to do. So that's why people came up with different ways to make this make it easier. Okay, I guess that's where we stop. Any questions?